Hello, everyone. My name is Oleksii, and I work as principal software engineer at Riot Games, mainly on League of Legends. Full disclosure, the topic that we're discussing today has absolutely nothing to do with my work, and all opinions of my own. And we're going to talk today about HTTP protocol, and specifically what I want to talk about is the following. We got the HTTP protocol established exactly 30 years ago. It was 1991, and it was a pretty interesting protocol at the moment when it was created. The protocol evolved over years and years, of course, because we discovered the internet changed since the time. I think you all understand that. But what's interesting in this perspective is that the pace of the changes were pretty slow from the very beginning. And now we got, I'm not sure if it's like exponential curvature, but it seems like it. So we got Websockets, and then Speedy, and then HTTP2 and HTTP3 almost in the course of like 5 years. So what I want to discuss today is basically, why do we have that many changes and why everything is moving so rapidly? What does it mean for us from the practical or implementational perspective? And specifically, I want to talk about if we can keep up with the pace from an implementation perspective, like developers of frameworks, or we don't. And just to talk a little bit about like what HTTP3 means for us and what it will bring, or already did. So I have a lot of information. I'm going to go quickly through everything up to HTTP3, and I will focus mostly on that one. If you have any questions, just write down in chat. I will check from time to time if there's something that we need to discuss right now, okay? Deal? So back 30 years, we got the first version of HTTP, even the before first version of HTTP. This is how it looked like. This is like everything you need. If you're like 30 years ago and you want to browse internet, you just need telnet, and you can connect to the Open TCP connection, emit whatever request, and get response back. And I'm still curious how many open tabs that could handle. We don't use this nowadays, unfortunately. But the protocol was that simple, and the idea was to get TCP and put request reply semantic on top of it with some specification of what request means and what replies means. A few years later, we got the new version of HTTP protocol, and it was mostly cosmetic changes. So like new method, content negotiation, something that browser needed it to make more like beautiful pages. The interesting change, we got optional host header because it became popular for one server to host multiple websites. So now if you connect to IP address, the web server doesn't necessarily know what it needs to reply back. And the most prominent change was the connection keep alive. And the idea behind this was the header. The TCP handshake was slow. It was slow, it's still slow. Like 30 years later, it's still slow. And when we didn't have much of the data on the internet, or didn't have like much of like traffic anyways, you were to send requests, you need to open TCP connection, and you need to go through all handshakes and then you close the connection. And it was slow and expensive. And the idea was, let's do connection keep alive as an option, which is the ask for the client to keep the TCP connection open to wait for the next request to be sent. A few years later, 1.1 was actually more of like that was like a real standard where it was like, okay, we're doing this anyways, let's just standardize what we're already doing. And host header became mandatory because everyone moved to using Apache web server or Nginx later, and they kind of worked based on host headers. We introduced 100 continue because we got systems that had significant data size, significant data volumes, and they need like some flexibility around this. So we got chunked, we got transfer encoding chunked, where you can send, rather than sending everything in one run, you kind of send it chunk by chunks. We got byte range. So we, instead of asking for the entire response, you ask for the part of the response. We introduced compression. All of that was because we got too much data there. What was interesting that we upgraded it, we got the idea of upgrade, which is when you establish the protocol here, you can see that you announce which version you're using. Now there was introduced, there is additional header that you can say send, where you can say, well, I'm using HTTP 1.1, but I actually want to upgrade protocol for something different. And that was used later for WebSockets. We will talk separately to this. The thing that happened in 1.1 is like connection keep alive became default. And that was the biggest change. The biggest change was that if you have something optional in your standard, it doesn't really work because no one knows if they can rely on this. So what we did, we said, okay, keep alive now is default option, and you have basically opt-out strategy. You can send connection close if you want the counterpart to force close connection. Another thing, previously, web service tried to do a thing that was called pipelining. Pipelining is was an interesting idea. It's like, rather than sending request, getting response, then sending another request and getting another response, you're saying, okay, I'm sending you 5 different requests and I'm waiting for 5 different responses. Why this was used and what was the idea behind this? That the idea was that if you open the page in the web browser and you have 5 images, and you don't want them to request one by one, and you also don't want to open 5 different connections because connections are expensive. So you're saying, I'm going to request all 5 of them and then just wait for 5 of them back, because now the server can optimize the transfer for me based on this, because server knows everything that I know upfront. Unfortunately, it didn't work out well. And nowadays, we pretty much no one uses this pipeline, and like it's not supported by most frameworks. First of all, it gives pretty bad tail latency. And another thing is, like, once again, that's optional. If something is optional in a standard, no one really knows if I can rely on this. And as the client, I don't know if the server supports pipeline. And so me sending multiple requests, I can break things, and that's it. So people like didn't use this. But this is the change. This is nowadays, if you're issuing an HTTP request, you have way more headers, way more information. Like you have like content negotiation, you have content plans, you have like, and what's interesting, you have this connection left intact, which is the keep alive option that's maintained by everyone. Now we're moving to more sophisticated protocols that was still built on top of HTTP. And the first sophisticated protocol was Websockets. And the idea of Websockets was that HTTP was the request reply from like very one-sided, like biased in terms of like, if you're the client, you're always the client. If you're a server, you're always the server. And from time to time, specifically when web evolved into things that we call now Web 2.0, I think, where we got this like interactions and we get chats and we get like notifications. There was an idea, there was necessity for you to create this bidirectional channel where client and server can send data in both directions, like choosing who's doing client and who's doing server part based on the context. And the protocol that was created for this was called Websockets. And the idea was to use HTTP upgrade header. So there was nothing pretty new in this. You set up the TCP connection, you set up HTTP session within this TCP connection, you send HTTP upgrade header, which looked like that, which is like you're saying connection upgrade instead of connection keep alive, you say upgrade to WebSockets. You send some WebSocket related headers, and the server replies to you. If it's okay, it replies to you with the new switch protocol status that was also introduced as part of HTTP 1.1 RFC, where this is like specifically, it says, okay, I'm accepting your upgrade and we're switching to a new protocol. So it announces the protocol that's now used for the conversation. There were a bunch of interesting things that happened when we introduced WebSockets, because there is a huge difference now in the application semantic. It's not like request reply only. So we also did a framing, like we introduced different frames. Like now you can specify if it's like text, binary, if it's like closed frame, or this is continuation, because now we're kind of back to TCP world where like you don't really know what frame means and you want to react differently on different frames. So it's like the text only protocol didn't really work out. And yeah, this is where things start to get dicey and way more complicated. From my take, the WebSockets protocol was actively used when it was introduced, but then less and less common. And we even introduced some simpler versions, like for example, server sent event, where you kind of want to maintain stream from the server, but you don't want to have to pay a price of full bidirectional duplex communication. And the foundationally, if you think about this, like what you get with WebSocket was you go through multiple layers of handshakes and this like negotiations. What are you actually doing to get back something that was looking like TCP? Because TCP is fully duplex bidirectional protocol. From the implementation perspective, WebSocket is fully implemented in Netty, it's supported in Aleph, and the dicey part in Aleph around the WebSocket was that Aleph follows WinSpec for request reply and for streaming bodies, for example, but there was no spec for WebSockets, and it was like not really clear what everyone should be using. In Aleph, if you have this WebSocket connection and WebSocket client for the server side and for the client side respectively, and what you can do on the server side, you can get the request and you can issue the upgrade. And this looks like that. You call WebSocket a connection on the request, and you get back manifold stream. And that's a natural representation of WebSocket, because this is what it is. It's a bidirectional stream where, and you can read from there, you can write there. The problem goes now into two different directions. First level of problems. WebSocket is pretty much transport layer protocol. It's not transport, it's like session layer, but the things that you're sending there and you're getting from there don't have application semantic. So if you're working with WebSocket, you can't do this like on the raw stream. You need to introduce application semantic. Your application on the both side need to understand what you're sending. This is like what JSON RPCs, this is like images, it's like text-based chat. it's like some events in your game or something, that's the protocol that you need to define on top of that. So you don't have this like nice and shiny request reply cycle. You need to think about this. And the second part was, now when you have bidirectional stream, you got all problems of doing bidirectional streaming that you always do have. Like, for example, back pressuring, or dealing with windowing, or dealing with buffering, or dealing with slow connections, or dealing with like dropping packets when you don't have enough space in your buffers. And a lot of this manifold solves a lot of the problems for you, but it still forces you to make decisions what to do in these cases. And this is the complexity that is like way hard to like, okay, request reply gives you kind of back pressure out of the box, so you don't need to think about those problems at all. If you want to know more about the in-depth of the implementation of WebSockets, you can check out my presentation. It was a few years ago, but it's still relevant, and it's still kind of good information there on like HTTP deep dive with Aleph and netting, goes through how it works in netting, how it's implemented in Aleph. Because of all of these complexities that we got from the streaming level protocol, some of the hardest issues that I worked for Aleph were around WebSockets, and some of issues that we backported it to Netty was also about WebSockets. And I think it's like hard to tell why it's the case. I think it's a less common protocol, so it's like less tested, less edge cases, and another level of problems was that Aleph has this connectionless API for HTTP1, and that's because we had this RIN spec, and the RIN spec is connectionless. You have something that looks like a client for you, but it actually doesn't mean the connection on the network side. It actually means multiple connections out there, and the client will do like the juggling of open connections for you. When it sends the request and you're waiting for response, the connection is clogged now in a way. You can't use it for the next up until the point where you read the next response fully. But you don't see this in API. An API is just like a function, and you get it, and you give it request, and you get back their future of response. So there's nowhere there the idea of the network connection. And that's like most frameworks do that. This is what you get from the simplicity of HTTP1 protocol. And this is, from time to time, it creates interesting edge cases, even for HTTP1, where, well, I need to track timeouts, I need to track cancellation, I want to track if the client was disconnected before I even started it sending response, I want to measure the idles there. All of that means that you can't do this on the application level. You need to do in the library, or otherwise the user just don't have access to connection. In WebSockets, this became much bigger of a problem, because now you don't have this concept of having a pool of multiple open connections. When you upgrade into WebSocket, you're basically hijacking the entire network connection. And this network connection not being presented in your API puts all problems like dealing with this connection on their application side, which is, yeah, it's just a leaky abstraction at that moment in time. And I know that there is RIN 2.0 spec out there in draft, and I know that there is a WebSocket there as the specification. I didn't go deep into the specification. I honestly, last time I did Clojure was like 2 years ago, so I'm somewhat far away from the state of their development there, but you can definitely check out draft and see what it tells about WebSockets. So overall, this is my personal spicy take. WebSocket is not an application level protocol, it's just a session level and session layer, and you need to create your application layer on top of that to get something meaningful out, which is a lot of work. Okay, moving forward. What we get later was TLS and the thing that we called LPN. And that was not the new version of HTTP. It was still HTTP 1.1. It's just an extension of the protocol. And TLS was their replacement for SSL protocol for security purposes and for a cryptography used to ensure the security of the connection. And what's interesting, TLS was the first example of like how hard to replace something that has like internet-wide adoption, which is like it took a lot of years for us to move away from SSL to TLS. But what was interesting is this ILPN, application layer protocol negotiation extension, that evolved and merged, I would say, from Speedy development. The Speedy was the protocol. It was the extension for HTTP that came out from Google and was used heavily to influence, it just influenced HTTP2 development a few years later. And the idea behind this, the LPN, was that HTTP upgrade is kind of cool to have as an option, but it's slow in terms of it introduces additional round trip. So you establish TCP connection, you establish TLS on top of that, you establish HTTP, and now you kind of need to go and say, okay, I want to upgrade, which is like +1 round trip. ILPN was like, let's do this. Let's kind of squash two of them together, and let's, while we're discussing things like ciphers and the key exchange to establish TLS handshake, let's also do this. You can see it's like offering H2, offering HTTP 1.1, which is, let's put into TLS handshake something that's not TLS related, but it's like, okay, I support multiple protocols, and let's negotiate this earlier. So we don't need to wait for another round trip. And the response would look like, yeah, server accepted it to use HTTP 1.1, which is, the idea is like, you're saying, I'm supporting this 5 protocols, and the counterpart tells, okay, I'm supporting that 3, and whatever is decided to be established. And now you don't need HTTP upgrade header, because when you establish TLS, you already knows what protocol you go with. That's a huge deal, honestly. Now, that was a really interesting take from that time. Then now we go to HTTP2, and HTTP2 was heavily influenced by Speedy. And so first, why? Why did we need the completely new protocol? Because you kind of get the idea, right? Between 1.0 and 1.1, there is not that much of a change. It's like mostly cosmetical, but it's like compatible and all the stuff. HTTP2 was not that. The HTTP was like completely new. And the idea was that, well, we still have TCP handshake, and it's still slow. And here is the thing: when you have to deal with more things that goes through the same connection, you have this with HTTP1, you have this head of line blocking, which is to say, if you have one open connection and there is someone in front of you who's like super slow, it makes everyone slow, because once again, you're sending a request, you're waiting for response. So while you're waiting for the response, you basically clog the connection, and everyone who's behind you, they need to wait for your response as well. So what it gives you this weird spike and tail latency, where everything goes like, okay, up until one thing breaks, and then everything goes to straight to hell because your tail latency latency now depends on the slowest part of your system. And that's not good. And the typical solution for that before HTTP 2 was we just open TCP connections. We just open tons of HTTP connections. The problem that TCP connection most of the time is implemented somewhere in your operation system, in your networking stack, like in your kernel. And each TCP connection that's a really expensive thing to do. And what we created just another problem with like opening those connections. Now the congestion control that's implemented on the side of TCP, it's really hard to do congestion when you have tons of open connections and they are kind of closing and like opening all the time instead of like keeping one connection alive. Like, for example, think about like you have this resize of the window, and the resize of the window works really well when you have one connection that leaves for a long time for you to understand what's the ideal size for the window. When you have this, like you open tab, the tab opens like whatever connections it needs to, and then you close the tab, it closes all connections. Like all connections, they're like short-living, and there's no way for you to optimize congestion because like, well, I guess I have no idea what's the best way to do TCP here. So all of that, more we had things on the internet, more we did with like, I think IoT, Internet of Things was one of the driver here, which is like, let's put all of our devices on the internet and see what will happen. Well, what happened is a new protocol. So the idea behind HTTP 2 was, once again, there were like a lot of things in there. Typically, it's like when you want to introduce new system, you're like, let's put all our new ideas there. So we got pretty much everything that you can think about, but the key part was this, the multiplexing over single TCP connection. So the idea was, let's introduce the idea of stream, and rather than have request reply in the over one connection, you kind of have virtually as many virtual connections within one network connection, and you can send request replies over those streams independently. So now if you have independent system, independent kind of actors in your system, instead of open new TCP connection, you open, you declare the virtual stream within the HTTP2, and the stack that implements HTTP2 for you is now responsible for multiplexing all of them over a single open connection. That was the key idea. Also, we got binary compression, which is like to say, okay, the compression is still a problem, and we've got like a text-based protocol for headers. Let's remove that. We introduce HPAC, which is like, let's do compression for headers. Let's do binary for everything. Let's introduce framing that we did for WebSockets once again, because now we have streams. So it's not like as simple as it was before. Let's introduce HTTP2 server push, which is now the server can initiate the stream, which is like server doesn't need to wait for client to ask for something, it can initiate. So we have bidirectional full duplex here. Because of all of this complexity, now we introduced ways to deal with this complexity. It's like settings management and priorities for streams. That's how it's done. It's like you have a separate stream that's like a system level stream where you exchange the settings, where you tell how many streams you want in this connection, what's the priority for each of them, what's the idle, what headers do you use in your dynamic table, and like, because you kind of need, if you think about this, the concept in HTTP 1 was, when you need something from the server, you just open connection, you issue request, and you read response back, and you're gone. And it's like a short-living interaction. HTTP2, a foundational idea is like you have a long-standing, long-living connection that's open there. That's the entire mean of your conversation with the server. So we introduce settings as the way, well, if when time passes by, you kind of want to change something and how this conversation is established, and rather than just dropping everything that leaves in that connection, you want to issue the change to like settings or change priorities or something, or close something or reopen. We used LPN because we already had, and as I showed previously, previous example, we used LPN where you can say, hey, I actually support HTTP2. Do you want to use the more modern version? But you can still do upgrade if you're like established one-on-one. You can do upgrade with like text only something HTTP2. That's not all. That was mostly used when we kind of did the migration, or we tried to do migration. It's not as used, not as actively used now as an option, but you still can do text only. Oh, and by the way, I'm not sure why I didn't mention this, but we said that cryptography only. There was the idea to ban non-crypto conversation, but that didn't work out super well. So we have an option of like do text only HTTP2 where you don't have any encryption on top of your transport layer. It's not the case with the new HTTP3, by the way. So HTTP2 is fully supported in native. There is an implementation of HTTP server and HTTP client and all utils that you need to kind of work with this. It's not supported in Aleph, though. It's not provided you out of the box. And again, the conversation, I think it was like 5 years ago when we talked about this in Aleph, and the conversation was that ReinSpec doesn't provide any notion of streams or server pushes. So it's like, it's hard to do an application level API that would be respected by all frameworks. And HTTP2 in this, if you want to introduce this in the application level, it would derail the implementation where now you're not compatible with other frameworks. And that's a huge leap, honestly. So we didn't add the support. And I mentioned that some of the hardest issue of work were about WebSockets. Honestly, that's because we don't support HTTP2, because HTTP2 is way more complicated protocol than WebSockets. And I imagine that complexity of Aleph would be completely different nowadays if we include it there. Another part of the conversation that we had over and over again was that how often do you actually use HTTP2 directly? And what I mean is that HTTP2 is fairly common nowadays. Like many websites use this, like all browsers support that. A lot of, like if you're using something like AWS load balancer, well, it supports HTTP2. The thing is, like, how does it work? It's not like you use HTTP2 in your application. It's there are some infrastructure proxies or load balancers that typically does what we call the HTTP2 termination. They accept HTTP2 from the outside world and they convert it to like plain old HTTP 1.1, which is the same thing we do like TLS termination on the load balancer. This is the typical for many applications. You don't want to deal with the problems of TLS or in your application. You don't interact with it directly. You put Nginx in front of you, or you put like Google Cloud load balancer or whatever, and they do this for you. They terminate TLS session and they go to you with the plain protocol. The same happened to HTTP2, to my best knowledge. Most of usage like that. There are some applications that heavily utilize it, but this is not as common. Another use case was gRPC, and I think gRPC made a huge boost in the popularity of HTTP2 and adoption of HTTP2. And it's like, I can be wrong here, it was like quite a few years ago, but it seems like there implementation in NATI was introduced because of the work on gRPC Java that was done in Google. And gRPC is the RPC protocol that uses HTTP2 as default, and I think it's the only transport. And once again, your application doesn't really know about HTTP2. You don't use HTTP2. You're using gRPC, and you're doing like streaming RPC calls or whatever you need to do, and you don't see what's out there. You don't know about the transport level protocol. At some point, it was interesting for me if it's like it's possible to do HTTP2 in Aleph, and this is a tweet from like 2 years ago, more than 2 years ago, and yeah, it's possible. And the idea that all components in native that you need to establish HTTP2 are there, so you can kind of combine it the same way that Aleph combines native components for HTTP1, and you can get pretty much working system. It's not even that hard. The problem that now to create a reasonable API for applications around it, that's a problematic part. But establish the connection and send something over this connection. It's pretty straightforward, though we never went further than this experiment, and we never did anything for like main branch of Aleph. That's the next personal spicy take. HTTP is rarely utilized directly from your application layer. It's mainly used for infrastructure, proxies, load balancers, or RPC systems that introduce another application level contract for you, where you don't deal with transport directly. You deal with like whatever RPC system is out there for you. Okay. Going next. That's I mentioned this like exponential, so we're going super fast now. It's like HTTP 3 now, and okay. So well, now what? That's the question. It's like, why the next protocol? And like, so HTTP 3 is less about HTTP. HTTP is almost not changed. It's almost HTTP 2. It's like limitation applied. We will talk about this, why, but it's pretty much the same as we get in HTTP 2. What's changed and what's different is that we decided to change the transport level. And for 30 years, we used TCP. Now the idea that we're going to use QUIC as the transport layer instead of TCP. So why we want to use something other than TCP? So there is the problem of head of line blocking that we talked before was around, you have HTTP connection, you send request, you're waiting for a reply, you're blocking everyone who's behind you, who's like waiting now. The problem that we introduced this logical streaming within Open TCP connection, the problem that TCP has still head of line blocking. It didn't go away, it just moved to a different layer. And the thing that if you think about TCP, what TCP is not like a magic, right? It sends the same datagram packets over IP for IP6 network, and it just counts the sequence of those datagrams and like what byte did you receive and like what's your offset. And if it didn't receive something or receive something in wrong order, it does reordering for you and it does retransmission. So it asks the sender to retransmit the packet that was lost. So the idea now is that logically you have independent streams in your HTTP2 connection, but your TCP level connection is still strongly sequential. If something goes wrong with this TCP, everything will be retransmitted and everyone will wait for this retransmission. You can't opt out from there. It's like, this is not the layer you deal with. It's not something you control. It's not even in your user space typically. So streams are not physically independent. They're independent only logically. Now, the different problem, we have still 3 levels of handshake, and each handshake requires at least 1 round trip, and from time to time they require more. And you establish TCP connection, you establish TLS, you establish HTTP over that if you're using some upgrades or something like that. That's painful. That's a lot of time that you need to wait before you can send anything. And it's better with TLS 1.3 because we squashed some handshakes, but that's still a bad thing. And TCP is hard coded into infrastructure that we have like links, routers, and kernels. So it's hard to do something new with TCP. It's like probably no way to do something new in TCP nowadays, because like you need to implement everything, and you can't. So the idea behind Quick was like, let's merge multiple layers of transport, and let's introduce, rather than using TCP and TLS on top of that, let's merge them into one layer and introduce the new UDP-based transport that does everything: handshakes, encryption, connection, and physical streaming. So now streams that we introduce in HTTP2 for logical level now goes to like, let's do transport level streaming. There is one interesting thing here. Let's not rely on IP. And there's one interesting problem. It's like that we never had before. That like, if you establish TCP connection, you rely on IP address to kind of define what's the, like, who's talking to whom. The problem is like, if you're, for example, you're using your phone, right? And you go and you use your Wi-Fi, you go outside and you switch to LTE connection that you have, well, your IP is lost. And now if you have like conversation over Zoom, the Zoom now has like troubles because the connection is lost, it's reestablished as the completely new connection. And now your application needs to be smart enough to manage this. The idea in Quick is like, let's do connection ID instead of IPs. So now you can switch between IP addresses, but maintain the same connection ID. So the application doesn't really know that connection changed. That's a cool idea. Unfortunately, it isn't really cool in practice, but we will talk a bit about that. Yeah, so the idea behind moving from TCP to UDP has some greatness is there. Like, for example, we can introduce whatever we need to do with retransmission and congestion and passing, but there is also downside, is like all of that was already implemented in kernels and the OSs and Linux, and people spent 36 years like optimizing that. Now we kind of want to do this from scratch or something, because that's unclear, because we want now to do retransmission in the user space, and that's unclear if we can get the same level of performance as we get from operation system previously. From the stream perspective, there's nothing new. It's just we're moving them into transport layer. We have bind unidirectional, we have initiated by any parties, and they are now physically independent. Now, HTTP 3, what we do, we get HTTP 2 with the previous semantic that we have for HTTP 2, with all of this like logical streams and settings and priorities and pushes, and we just put in the new transport, and now we kind of connect logical stream to physical streams in the transport layer. And the only interesting thing that's changing now is like QPAC instead of HPAC, because so previously you have this a way to compress your headers where you had static table and dynamic table, and you can announce what headers you're going to use, and you can like do a really good compression for this. The problem now is that there is no guarantee of there, because like all streams are independent physically now. There's no guarantee in which order you will get information from the counterpart. So you kind of need to deal with this problem. And the dealing with this problem means that you can get header before the header was announced. So we changed the way the dynamic table works in the QPAC. We'll talk about a little bit what it means from an implementational perspective. And another problem, if we want to squash all of our handshakes together, like how would we announce that we support HTTP3? For example, you go in the website and you have like browser open the page, how the browser knows that to get something, it can use HTTP3. And the proposal was to use alt CSV is like a special tag in HTML that you can say, or like special header that you can put in your response, where you say, okay, anytime, next time you're going to call me, use HTTP3 from the very beginning. And the problem now is like none of the like LPN doesn't really work, upgrade doesn't really work, because you want this as like your very first connection establishment should be different. And you kind of, that's a major issue. It's still a major issue. It's like, it's unclear how we're gonna even pull something like that off. Putting all of this in context, Quick is a transport layer, so it's not only for HTTP. There are some initiatives there to make like MQTT5 works over Quick, DNS over Quick, and more of them. And it's not the first UDP attempt, honestly. We had some WebRTC implementation over the UDP, so we'll see how this one goes, right? And this was my tweet from also 2 years ago, where I'm like, okay, can we do Quick and Aleph? Yes, we can. And this was a really interesting experiment. The interesting was that I used the datagram. So I used Aleph UDP as the transport layer, and I used some weird Java library. I tried to remember which one. I honestly don't. I couldn't find it. That did a re-implementation of all crypto functions from OpenSSL and some additional crypto functions that I had to use for Quick first, because like Quick is like an encryption first. So it's like everything is encrypted, including your first messages, your first packets. So I had to use that one. It was definitely not the option where you kind of want to standardize over this, but it was a nice experiment and it worked out pretty well. This is my tweet from like almost a year and a half later. And here what I did, what do we got over year and a half? We got less dark theme and Vim instead of Emacs. But the idea here was that I took the Cloudflare quiche library, which is in Rust, and that does Quick and HTTP3 on top of Quick. And it's a really good library in terms of like, it provides API to really be like low-level library. And what I did, I implemented the GNI layer on top of this library using Rust GNI, also in Rust, and a Java API on top of GNI calls. So open source, this is like quiche for J, which is Quick and HTTP in Java. And this is libraries, this is on GitHub. You can definitely use this from Clojure, just dealing with like Java in the ROP. What was cool about this is that they provided it all encryption, and like everything that you need to make Quick happen, but with the pluggable IO, which is like the library doesn't force you to use specific IO scheduling. And I think that default implementation was done in just threads. And as an example, I implemented a Netty event loop just to show how to plug your own IO scheduler or whatever you have out there. So I honestly don't work on this library actively nowadays, mainly because Norman did something similar, and I don't want to take credit. Norman did most of the work, pretty much entire work here, and he created a Netty incubator called Quick and HTTP3, which basically does the same. It's the native Java layer on top of GNI's written on top of Cloudflare's quiche library. So this is still an incubator, so it's not the official part of Netty, but contributions are always welcome, and there are quite some work there still to make it final. So from the implementation perspective, Quick kind of looks simple. You have a typical for any like network library, you have like connect, accept, send, request, or like send stream and request stream. This is new. This is not something you have in TCP. But when you go into details, that got like really gray and dicey. And first of all, it's like cryptography first. And boring SSL provides a new API. They upgraded the library and said, hey, this is the cryptography you need to make Quick happen. OpenSSL does not provide because Quick's still in draft. And OpenSSL decided to wait for Quick to go out of draft state before introducing new APIs in OpenSSL. You still can do this in OpenSSL, but it requires you quite some manual processing, so it's not as straightforward. Framing in this transport is straightforward and simple. The hard part now is like loss detection and congestion control, which is like take all of your TCP stack that's implemented somewhere in your kernel and re-implement it from scratch. That's hard. And Cloudflare Quiche provides two different implementation, which is Reno and Cubic, and there are different algorithms. You can learn, you can read on them, on like there are multiple resources that provide information why they're different, what do they provide. But that's honestly, that's like a pretty deep conversation on its own. The connection migration between IPs that we talked about, where you can use connection ID instead of IP, that's interesting idea in practice. It's like in practice, it's really problematic because most frameworks that we have out there, they kind of build around the idea of having IP addresses. Even in NETI migration, I think even Quiche still doesn't support this. After like 4 years of active development, Quiche doesn't support the migration between IPs. And we'll see how that will play out. It's like we have such a deep connection to IPs that it's not obvious how to do it. So from HTTP 3 perspective, QPAC is pretty much similar to HPAC. Instead of like the only thing that's there is like dynamic table and dynamic. I mentioned the algorithm for dynamic headers exchange now is extremely complicated, and the state of implementation after 4 years in Quiche is like to implement dynamic tables in Quiche. If you want, the contribution is definitely welcome. And there is an open ticket that I opened again for NETI incubator package, which is like let's support dynamic table. That's a lot of work. If anyone is looking for something to contribute to, that's would be much appreciated. So in general, what it means for all of us and from our use cases is the idea that, so here's my take. If you don't know why would you need Quick or HTTP 3, you probably don't. It's the same conversation we had with like HTTP 2. If the load balancer solves your problem, you don't need to even think about this. And the same for Quick. I think the Quick kind of promises you a lot, but if you don't know why it would be useful for you, it probably won't. The thing I'm working for games, for example, for gaming company, and we know that like games don't use HTTP, they don't even use TCP because TCP is the luxury we can't afford. It's like too expensive. So we, like most games, they have some homegrown UDP protocols that do solve most of the problems that Quick tries to solve with their streamings. And you kind of know, obviously, you read through Quick and you're like, yeah, of course, yeah, it's like that's a known issue, and yeah, we kind of we had to do something to solve this as well. If you probably for many applications, it's just irrelevant because TCP work and HTTP work pretty nice. If you have high throughput requirements, you can have more than a request reply, like you do streaming out. The thing that I do a lot, which is like a high throughput telemetry ingestion. That's an interesting use case. Request reply is really not the way you want to go, so you're kind of looking for something more expressive in that perspective. And if you have something where too many things happen within the same connection, once again, you can get something from Quick. But overall, we'll see how that one will play out. And that's pretty much everything that I want to talk about. Please connect with me on Twitter or GitHub. And if you have any questions, I'm more than glad to answer.